Yeah, so my name is Haikarainen, and just thank you for the presentation. I'm from the Laboratory of Process and Systems Engineering at Akademi University. And yeah, I'll be talking about an optimization modeling approach for modeling the transition of a steel plant towards hydrogen-based steel making for the use of analysis of such a transition. So I'll start by giving a brief overview of first the traditional kind of coke-based reduction, and then this hydrogen-based reduction as a potential kind of future possibility. And then I'll explain kind of the motivation and idea behind this optimization model that we have, and then I'll give some examples, give some example solutions, and kind of show how we can use those for some analysis. But I'll start with a very, very, very simplified explanation of steel making. So the two basic ingredients traditionally are coke and iron ore. And this coke, of course, is a form of processed coal, and this iron ore contains iron oxides. So these are fed to a blast furnace wherein the carbon in the coke reacts with oxygen to form carbon monoxide. And then the iron oxides are reduced by this carbon monoxide to iron and carbon dioxide, forming an intermediate product called hot metal, which is fed to a basic oxygen furnace where excess carbon is removed from the hot metal to produce liquid steel, which is then further transported to kind of casting units and rolling mills to produce steel products. Now we can already see here that already this basic chemistry involves the formation of carbon dioxide. And as was previously mentioned here today, about 7 to 8% of global carbon dioxide emissions stem from steel making. So we clearly have kind of an issue here with this carbon dioxide. So a future possibility would be to replace this coke with hydrogen as a reductant, and let it react in a shaft furnace together with the iron ore. So the iron oxides are reduced by the hydrogen to form iron and water, or steam. Creating then the output would be direct reduced iron, which can then be fed to an electric arc furnace, which again melts this reduced iron and produces liquid steel. So if we compare these two processes kind of energetically, you can see that here in the traditional path, this traditional route, the main energy source is coal. Whereas here in this alternative route, the main energy source, both in this electric arc furnace, it is electricity. And then, as we have heard today, one major path of producing hydrogen would be through electrolysis, again using electricity. So as long as we would have access to green or emissions-free electricity, we could get rid of most of these carbon dioxide emissions in this process. And that would be great. And none of these kind of, the shaft furnace and this electric arc furnace, there are kind of already existing technologies for them, which are very much in use. So if today, about 70% of steel is produced using blast furnaces, so about 30% is produced using electric arc furnaces. But the main raw material would be steel scrap or recycled steel. But of course, there's not enough recycled steel in the world to cover all of the steel demand that we have. So we also need some other route to producing this kind of fresh steel. Shaft furnaces are already in use to produce direct reduced iron, but the raw material is mostly natural gas, which is reformed into carbon monoxide and hydrogen. So it's also a kind of a fossil-based process today, mostly. But the same type of shaft furnace can be used with mostly hydrogen as the reactant gas. So this kind of tested and possible. But then again, if we look at the entire steel plant, we're not only dealing with these furnaces. We also could have a coke plant, maybe power plants producing electricity and heat, air separation units producing oxygen, casting and rolling mills. And a steel plant today might be very highly integrated and optimized So we use the different process flows and process gases and materials and energy, both within the plant, and we might be connected with industries in the vicinity or outside this kind of steel plant system, communities producing like district heat for communities and such. So how now, if we plan to replace two of these fundamental units in a steel plant with two different types of units, and maybe add other units like electrolyzers or other forms of producing hydrogen storage, maybe a pelletizing plant that would need another type of pellets for the iron ore, other type than blast furnace pellets. So how then, during a transition that may take decades, such a transition to completely transition to this hydrogen based reduction, how could we continue this type of integration and interconnectedness between these different units, both during and after a transition? So that was kind of the idea. Could we have an optimization model where we start kind of from a current point at a steel plant and then optimize this entire time horizon for a couple of decades forward, and kind of to get ideas of what could be feasible solutions for kind of intermediate steps before transitioning to kind of a hydrogen-based reduction, if that would be kind of an optimal case, given different options. So we wish to optimize this kind of pathway from current situation to a future situation. And we do that by kind of optimizing the investment and operation over selected time horizon divided into time periods. In practice, I use 5-year periods for, let's say, 25 years. So we need mathematical models of these different units, like the furnaces, the blast furnace and the shaft furnace, maybe the electric arc furnace, and then the process flows between, and then build up this kind of a overall system model to optimize, minimize costs or emissions over this entire time horizon. Regarding these more detailed models, we have, for example, a model of a shaft furnace where the hydrogen reduction takes place. And we can see from these kind of analyze constraints for these processes that we can then build into this kind of system model as well. We can, for example, see that in this shaft furnace, this top gas that exits the furnace might contain up to 80% of unreacted hydrogen. So there's clearly no need for hydrogen recycling in the shaft furnace process. So that's kind of an issue in itself, how to do that in an optimal way. And we can see, for example, that rates of fresh hydrogen needed for this process would be at least above, let's say, 40 kilograms per ton of DRI. And we'll see in these examples how that then adds up for the total steel plant. But then when we have a more detailed models, we need to simplify them. We make these linearized or almost linearized regression models that we then can build into a larger system model to make it actually possible to solve these models. Regarding the time horizon that we use, so we can, for example, start with a situation at a steel plant where we start from two blast furnaces, a configuration with two blast furnaces. Then we might expect that maybe after 10 years, one of the furnaces is decommissioned or needs to be realigned. So we can have that option as well. And then after 20 years, the second furnace is kind of decommissioned, potentially. So again, the question is, when during this time horizon should we invest in, let's say, an electric arc furnace or electrolysis, shaft furnace? How many of these units do we need? What should be the capacities of the individual units? And also importantly, how could they operate together with this existing units? Like, can the power plant continue its operation during this transition, and such questions? So we minimize accumulated costs or emission during the entire time horizon, kind of optimizing these operation schemes for like 1 year at a time. We assume like a constant production rate over each year. And then we kind of let the optimizer decide kind of investment decisions when to build what during this time horizon, and see what type of feasible solutions we can get. So for example, if we have an example where we have a steel plant which produces 260 tons of steel per hour using 2 blast furnaces, as in the previous slide, and we don't give it the relining option. In this example, I kind of enforce this hydrogen reduction solution. So also electric arc furnaces are charged with hydrogen reduced DRI and no scrap in this solution, just to see kind of what do we end up with, what type of solutions do we get if we really want to move to this hydrogen reduction option. I vary electricity costs, so we get different solutions here, depending on the electricity cost assumed. And we see here in this graph the operational cost as euros per ton of steel. So we see here that for electricity costs for 50 euros per megawatt hour or more, the operational costs will start increasing as we transition towards this hydrogen-based reduction. But with lower electricity costs, we can expect operational costs to start decreasing. And we can kind of see more clearly what happens in these different solutions when we look at the specific emissions in these different solutions. So we see here that in each of these solutions, we start from the same point where we have 2 blast furnaces, and we end up at the same point where these are replaced by 2 shaft furnaces and 2 electric arc furnaces. But what happens in between is different in all of these solutions. So with the most expensive electricity cost, we see here that after 10 years, when the first blast furnace is decommissioned, it is replaced with a shaft furnace and electric arc furnace. And then after 20 years, we also replace the second furnace. And the only difference with this middle solution here with the 40 euro per megawatt hour price electricity cost is that we move more of the production to this hydrogen-based reduction. We build a shaft furnace with a bigger capacity. And this kind of leads to these decreased emissions after 10 years. With 30 euros per megawatt hour, then we already get a situation where already after 5 years, one of the blast furnaces is replaced with a shaft furnace and electric arc furnaces, as this is already kind of economical with these lower electricity prices. And then with 20 euros per megawatt hour, kind of the most economical solution here, given the options that we have here, is to directly replace both blast furnaces with 2 shaft furnaces and 2 electric arc furnaces. So with these, we see this type of different configurations in these solutions. And in each of these kind of time periods, I remind here again that one time period is 5 years. So we have a time horizon of 25 years. So here after, let's say 10 years in this solution with 40 euros per megawatt hour, we can make this analysis of which units are kind of in operation or not, how the power plant is run, or how the shaft furnace is run. We can make this type of more detailed analysis as well. And we can compare this accumulated costs and emissions during this optimization. So here, even though we start at the same point in all of these solutions and we end up at the same solutions, so comparing with a situation where we would have continued using blast furnaces, we see that in this most expensive solution, we had a 20% lower accumulated emissions over this 25-year period. While if we directly move to this hydrogen-reduced production of steel, then we get almost 50% lower emissions. Given that I here have assumed emissions from electricity according to current levels of grid electricity emissions in Finland. How this translates to hydrogen use. Here is a graph with saying that if we with the same solution that we just had, if we replace both blast furnaces with shaft furnaces running on hydrogen, we would need about 24,000 kilograms per hour of hydrogen. And we can compare that with hydrogen production in Finland in 2020. This 24,000 kilograms would equal to about 210,000 tons per year. That is almost 1.5 times the total dedicated hydrogen production in Finland in 2020. So this kind of gives an estimate of the kind of volumes involved, there's really a considerable amount of hydrogen that would be needed for this steel production if we completely replace it. And then also, of course, if we produce that hydrogen with electricity, we need quite a large amount of electricity. So we could also, in this type of analysis, kind of look at the time scale here, kind of how quickly would it be realistic to build up this sort of hydrogen production, and we could build up constraints regarding that into the model as well, and take that into account. So, if I briefly give another example here, if we give more freedom to the model, that is to say, instead of kind of forcing this decommissioning of blast furnaces, we give the opportunity of relining them at a certain cost after 10 and 20 years. And then we also give the option of charging electric arc furnaces with steel scrap bought from the market, and also DRI that is imported. So I limit the amount here of imported scrap to 150 tons per hour. And then we get this sort of a solution. So regardless of electricity cost here, we could reduce the operational cost with the cost assumptions that we have in these examples, because these kind of the opportunity, the possibility of replacing a blast furnace with electric arc furnace and charging it with scrap is kind of the most economical option here, given the cost assumptions that we have here. So in both of these solutions with the blast furnaces replaced with an electric arc furnace fed with scrap and some imported DRI, replacing one of the blast furnaces. But we then note that one of the blast furnaces is realigned at the end here. So we continue using the blast furnace as well. But then with the cheapest electricity cost of 20 to 30 euros per megawatt hour, then we would replace the blast furnaces with a shaft furnace and 2 electric arc furnaces. So this kind of, in this solution, again, the shaft furnace option, this hydrogen reduction becomes economical compared to the blast furnace option. Yeah, accordingly, yeah, exactly. So the main point here, I guess the main point here with this electric arc furnace is that we all the time here compare also not only with replacing these blast furnaces with this hydrogen reduction, but we also need to account for this steel possibilities of recycling steel. But again, not all of the steel can be recycled, or it doesn't cover all of the steel demand, the global steel demand. So there's still kind of need for this hydrogen reduction and that process. But with this sort of tool, we can analyze the different types of, it seems like a viable way of making this sort of analysis with for different steel plants, with different options, different alternatives. But then we also have to keep in mind that any kind of forecasts on this costs and assumptions regarding costs and the technological process for the parameters that we use in these models, they're highly uncertain. But again, with a good model, or with a practical model, it's easy to kind of make a large number of different scenarios and compare them and the solutions that they give rise to. Some image trace here still, and then thank you.